I'm Brandon Seymour, and this is AI in 5, where we break down complex AI infrastructure topics in 5 minutes or less. Today is going to run a little bit longer, but I think this is an important conversation. Today I want to share what I learned from comparing AMD ROCm and NVIDIA CUDA in my local AI lab. I tested the AMD Radeon AI Pro R9700 against the RTX 3060 using the same local inference workflow. This was my first AMD GPU. At first, I thought this would be a straightforward GPU conversation. I expected the newer card with more VRAM and more compute to simply be faster. This is not what the testing showed. The R9700 was faster in several important areas, especially sustained generation and heavier prompt processing. But the RTX 3060 remained surprisingly competitive in the first response latency. The concurrency exposed something even more important. The runtime and the serving configuration were shaping the results just as much as the hardware. So this presentation is not really about declaring one GPU the winner. It's about understanding the entire inference stack and what actually determines the user's experience. The first result that changed how I looked at the comparison was the faster GPU did not always feel faster. This was the result that really started the whole investigation. I ran the same model on both GPUs, and once generation began, the R9700 produced tokens faster, which was kind of expected in my opinion, but in several scenarios the RTX 3060 returned the first response sooner. At first, that seems contradictory, but it really is showing two different measurements. Throughput tells me how quickly the model generates tokens once it's running. Time to first response tells me how long the user waits before anything appears. Those are not the same thing. A GPU can have a higher sustained throughput and still lose the first token race because startup, prompt processing, scheduling, and runtime behavior all happen before generation begins. This is why a single benchmark number can be misleading. We need to ask which phase we are measuring, which metric matters, and what the actual workload looks like. The goal of this lab was not to see which card was faster, it was to understand why the results changed depending on how the model was being used. To make that comparison useful, I first needed to control as much of the test environment as possible. To keep this comparison meaningful, I tried to hold the software path as consistent as possible. On the AMD side, I used the Radeon AI Pro R9700 with 32 gigs of VRAM, ROCm 7.2.4, Ollama 030.11, and AMD SMI for telemetry. On the NVIDIA side, I used the RTX 3060 with 12 gigs of VRAM, CUDA, matched Ollama version, and used the NVIDIA SMI for telemetry. Both systems ran Gemma 3 4 billion parameter with 16K context window. I tested baseline decode, prefill, time to first response, prefix caching, and concurrency. Both systems ran, one important detail is that Ollama num parallel was set to 1. At the time, I thought I was testing multiple concurrent requests. Later, that setting became central to understand the results. I also want to be clear that this is a directional platform comparison, not a perfectly matched GPU shootout. These cards are different in age, class, power, memory, and capacity. There is also a data quality caveat that I need to talk about. I reran the AMD test after restoring Hugging Face authentication and confirming the native Gemma tokenizer. The NVIDIA baseline still needs to be rerun under those exact match conditions. So the findings are useful, but being careful not to overstate what they prove here. Before looking at the results, it helps to understand the two main phases of inference, prefill and decode. Before the benchmark results make sense, it helps to separate the two main phases of inference. The first phase is prefill. This is when the model reads the entire prompt and builds the attention state it will be using during generation. Prefill is highly parallel and compute heavy. So as the prompt gets longer, the GPU has more work it can process in parallel. The second phase is decode. This is where the model generates the response one token at a time. Each token depends on the one before it, so this phase is much more sequential. That is why prefill throughput and decode throughput can tell very different stories. Then there is time to first response. That is the delay the user actually feels before the first word appears. Time to first response includes prompt processing, scheduling, queue position, so it is not controlled by raw GPU speed alone. The KV cache also matters because it stores attention state from prefill. When part of the prompt is reused, the runtime may avoid recomputing that cache section. The key point is that optimizing the wrong phase can give you great benchmark numbers while still producing a slow user experience. With that distinction in mind, the first result to look at is baseline decode throughput. This is the first direct performance result. At Concurrency 1, the R9700 delivered about 82.5 tokens per second compared with about 70.7 on the RTX 3060. That is roughly a 17% advantage for the R9700 in baseline decode throughput. When I increased the concurrency to 4 requests, both platforms slowed down. The R9700 still led about 68 tokens per second compared to about 61.7 on the RTX 3060, but the advantage narrowed to around 10%. So the AMD result was real. ROCm was not simply functional, it was competitive and in this test faster. But the narrowing gap under load was also important. If the hardware were scaling cleanly with more concurrent work, I would expect aggregate throughput to rise or at least remain more stable. Instead, both platforms lost throughput. That was the first indication that the runtime request scheduling behavior were starting to shape the benchmark as much as the GPUs themselves. The R9700's largest advantage appeared when I increased the amount of prompt processing. This is where the R9700 really started to separate itself. When I increased the prompt to 8,000 tokens, the R9700 delivered roughly 29% higher prefill throughput than the RTX 3060. That matters because prefill is the phase where the model processes the entire prompt before generating begins. Unlike decode, prefill is highly parallel, so the larger the prompt becomes, the more opportunity the GPU has to use its available compute and memory bandwidth. This is also where the R9700's 32 gig of VRAM became important, not because the VRAM automatically makes the model faster, but because it gives more headroom for larger models, deeper context windows, and future concurrency tests. The RTX 3060's 12 GB VRAM handled this 4 billion parameter model, but it gives less room to grow. For practical workloads like document summarization, RAG with large retrieval chunks, and long context assistance, the R9700's advantage became much more visible than it was in simple single-turn chat. But even with the R9700's leading in heavy prefill, the user experience was still determined by throughput alone. This slide shows why throughput alone did not tell the full story. Time to first response is the delay between submitting a request and seeing the first token appear. That is the pause the user actually feels. In the baseline and prefix cache scenarios, the RTX 3060 responded sooner. even though the R9700 had higher overall throughput. But as the workload became heavier, the results shifted. With a large prompt, the R9700 was slightly faster. In long context tests, the gap became much more noticeable, with the R9700 returning the first response in about 3.05 seconds compared to roughly 3.5 seconds on the RTX 3060. At higher concurrency, both platforms became much slower, which points us toward the runtime and queuing behavior rather than a simple GPU comparison. So the lesson here is that faster depends on what the user is waiting for. A platform can win on token generalization, but still lose on first response latency in smaller workloads. The workload shape determines which advantage actually matters. The next result was even more important because a software setting improved latency more than the hardware difference did. This was one of the most useful findings in the entire test. I enabled prefix caching without changing the GPU, the model, or the runtime. On the R9700, time to first response dropped from just over 3 seconds to about 1.45 seconds, which is a reduction of roughly 53%. The RTX 3060 showed an even larger percentage improvement, dropping from about 3.52 seconds to roughly 1.22 seconds. What is important is that decode throughput barely changed. On the R9700, it moved from about 78.6 to 80 tokens per second. So caching did not make the GPU generate faster. It avoided repeating the cached portion of the prompt processing work. That matters for enterprise assistance, RAG applications, policy documents, schemas, and large system prompts where much of the context is reused across requests. The lesson for me was that software optimization can improve the user's experience more than simply moving to a faster GPU. But when I increased the number of simultaneous requests, the software layer created a very different result. This was the point where the benchmark stopped looking like a pure GPU comparison. I increased the concurrency from 1 request to 2, then to 4. I expected total throughput to increase as more requests were introduced. Instead, both platforms declined. The R9700 dropped from about 82 tokens per second at concurrency 1 to roughly 68 at concurrency 4. The RTX 3060 dropped from about 71 to 62. At the same time, time to first response increased dramatically. By concurrency 4, users were waiting roughly 7.5 seconds before seeing the first token. And that pattern is important. The system was not producing more aggregate work or concurrency as concurrency increased. It was creating more waiting. The result was consistent with request queuing under the tested Ollama configuration, not demonstrated GPU throughput ceiling. So this was not an AMD problem or an NVIDIA problem. It was a serving policy finding. The benchmark was showing me at the runtime that the runtime was shaping the user experience just as much as the hardware. This next slide explains the Ollama settings that helped create that behavior. This is where the Ollama configuration became central to the story. Ollama is excellent for local experimentation because it makes it easy to download a model, start it, and begin testing within minutes. But ease of use and production grade serving efficiency are not the same thing. In this test, Ollama num parallel was set to 1. That limited the model to 1 actively processed request at a time, while additional requests could wait in a queue. That explained why concurrency increased user wait time without increasing aggregate throughput. The screenshots on the right confirmed that the model was loaded on the GPU with a 16K context window. So the issue was not the model had fallen back to the CPU. The important point is that the concurrency 4 result did not establish the maximum capability of the GPU. It primarily showed how this Ollama configuration scheduled requests. For me, the broader lesson is that runtime selection and configuration are architecture decisions. They need to be designed and tested with the same care as compute, storage, or networking. That's why CUDA versus ROCm cannot be reduced to a single performance number. This is the clearest way I can summarize the platform comparison. NVIDIA and CUDA were still the easiest operational path. The ecosystem's broader, the documentation is more mature, and most AI tools are built and tested on CUDA first. The RTX 3060 also remained competitive in selected first token latency test, even though it was the older and smaller card. Its main limitation was capacity. With 12 gigs of VRAM, I have less room for larger models, deeper context, and multiple workloads. On the AMD side, the R9700 delivered the stronger raw performance. It was about 17% faster in baseline decode and nearly 29% faster during the 8K prefill test. Its 32 gigs of VRAM also creates much more room for future testing, which I'll be doing, but ROCm required more work. I had to align operating system, kernel, drivers, permission, and runtime before everything worked correctly. And the extra VRAM did not make the card 3 times faster. The 4 billion model used less than 5 gigs of RAM. So this is not a one number decision. The right platform depends on whether you are optimizing prefill, decode, first response, latency, context capacity, concurrency, or ecosystem capability. To separate the hardware from Ollama serving behavior, the next step is to repeat all these tests with VLLM. So the next step is not to buy a faster GPU, it's to change the serving runtime. The concurrency result suggests that the tested Ollama configuration was limiting how requests were scheduled, so I need to run a runtime designed for higher throughput serving to test that hypothesis. That's where VLLM comes in. VLLM uses continuous batching, page detention, and chunk prefill to manage request and KV cache more efficiently under load. The plan is to repeat the same concurrency ladder at 1, 2, and 4 requests, then compare long prompt behavior, prefill caching, and both CUDA and ROCm paths. The important caveat is that I have not proven VLLM will perform better yet. If concurrency scales better under VLLM, that would support the idea that the original Ollama configuration was limiting the result, but difference could also come from kernels, model formats, quantization, or cache behavior. So the next phase is about separating hardware capability from serving policy. And that leads to the final lesson from this lab. Benchmark the entire inference stack, not just the GPU. So this is the main takeaway from the entire lab. The GPU matters, but it's only one layer of the inference stack. The first layer is the hardware itself, compute capability and VRAM capacity. Those determine what the platform can support, but they do not guarantee the user experience. The second layer is the runtime, scheduling, batching, cache behavior, and had a major impact on both concurrency and time to first response. The third layer is the workload, prefill heavy, decode heavy, cache reuse heavy workloads favored that platform differently. And the fourth layer is configuration. In this case, Ollama num parallel equals 1 shaped the concurrency result. That was not a GPU limitation, it was a serving decision. So the practical lesson is simple. Do not select an accelerator from a single benchmark number. Run the actual model with an actual context size, runtime, cache policy, and concurrency level you expect to support. The faster GPU cannot fully compensate for an under-designed serving layer. Before you buy the hardware, benchmark the complete inference architecture. I'm Brandon Seymour, and this has been AI in 5. If this was helpful, please like and subscribe to the video at my channel for more practical AI infrastructure conversations. And if you want to read more about AI enterprise, and the architecture behind it, visit me at virtualizationvelocity.com. Until next time, when I test out the concurrencies test with VLLM, we'll see you soon. Thank you.